quick review of 7.1 to 7.5. A couple of things. Hey, if you see a function, you know that any part of the function that's above the x-axis, we say that that's where the function is positive, because it's the y value of the function that is the function. So negative values, positive above the line. That becomes important when we're dealing with first derivative functions that are below the x-axis. That's where the value of the first derivative is negative. So the slope of the tangent lines on the original function are negative. But here's what we're going to do. Whenever we can, we're going to avoid the first derivative function on a graph and the second derivative function on the graph. We're going to get in the habit of converting those to the first derivative charts and the second derivative charts. It makes life easier for us. So let's go through and let's see what we're talking about. So first of all, this guy, let's make a first derivative chart and a second derivative chart. If we recall, the first derivative is going to be 0 at any min or any max because the tangent lines will have slopes of 0. So that helps us find the important values on the x-axis, 1, 2, 3. So negative 3 is 1. We're going to have a critical point at 1. And we're going to have a critical point, let's just call it 4. Let's just be happy, we'll call it 4. All right, so here's the deal now. The original function, do we agree the tangent lines have negative slopes leading into this min at negative 3? So we'd have negative slopes. After that, the tangent lines all have positive slopes. We could say, hey, look, positive slope, even up here, all positive slopes, so that's positive. Then they're negative, then they're positive. So that makes life a whole lot easier for us when we look at this first derivative chart and we can tell what the slopes are doing in the different intervals. Second derivative. We know that when the second derivative is 0, that's where we have points of inflection. So if we look on this graph, we can pretty much see that we have a point of inflection somewhere in here. Let's just say it's right at negative 1. So there's a point of inflection at negative 1. And then it goes from concave down to concave up somewhere over here. Let's say that's approximately a 2 on the x-axis. So that's where we have concavity. So the second derivative, prior to where the concavity changes at negative 1, we're concave up. This thing is bending upward right here. So it's a positive concavity. At negative 1, it's concave down. So this is negative. And then after 2, it is concave up, so it's back to positive. So we want to be able to make these first and second derivative charts and get comfortable with them going both directions. Well, draw a possible function of a f of x function from the chart that we have right here. So what we'd say is, well, okay, we've got negative 5 and negative 1, so we've got our y-axis there. Here's our x-axis. Here's negative 1, negative 5. Right here, positive 6, let's go over here a ways, positive 6, positive 8. All right, now think this through. This first derivative is going to give us the slope of the tangent lines. So negative 5 is a critical point because the first derivative is equal to 0 at negative 5. So negative 5, because it's got positive and negative slope around it, it's either going to be a min or a max. Hopefully we realize that the slopes are positive on the function until we get to negative 5, and after that they're negative. So this function must be coming upwards to 5 and then hitting a max, and then it's coming back down. Negative slope until it gets to negative 1, and then the slopes go positive. So there must be a min at negative 1, and the slope goes positive until we hit 6, another max. And so it's going to come up here to 6, and then it's going to drop down, hit a min at 8, negative slopes, and then after that, it's going to go positively sloped after that. Now, when we just say, like, sketch a possible function for that, we don't know how high or low this thing goes. That's one possibility. We don't know how drastic the mins and maxes go, but you could have another function on here that would do pretty much the same thing. And it might be down here, so it would go up and max at that, it would come down here, it would go up and hit a max at 6, then hit a min at 8, and go like that. That's another possible function. So we don't know where it is on the in the y direction because we don't know anything about the constant term of the original function. Anyways, hopefully that makes sense, but use those first derivative charts to think through what the slopes are like leading up to and following these critical points. All right, keeping that in mind, let's go to this guy. If we see this first derivative chart, we see that the slope's staying positive before and after this critical point. So this critical point is not a min or a max. This bad boy is one of those horizontal inflection points. So what we have in the function, if we sketch a possible function, zero's right here, let's put the y-axis there, and let's just pretend we know where this puppy's going in the y direction. We have a negative slope until we get to a min here. We can even write it down. We can say, look, we got a min here, we have inflection going on here, then it's going to be a positive slope and a negative after that, so this guy must be a max, and then it's going to come negative slope and positive, so this guy must be a min. So if we just keep that straight, then we got it made. We go to -2, we got 0, we got 3, and we have 7. So we can say, okay, we got a min at -2, so this puppy's coming down until we get to 2, so we could have the function coming down to 2, and we have a min here somewhere, and then we have a horizontal inflection point at 0, so it's got to come up and bebop at 0, but keep going positive until we get to 3, where we're going to find a max, and then we're going to bring it back down to 7 where there's a min, and then go like that. So that could be a potential graph right there. So just think things through from the chart, and even label them like this just to keep it straight, and then go chart it. And again, we could be anywhere in the y direction, so there's just one possible sketch of the function f of x. Then we get to something like this, sketch a graph of f of x from this guy, which we're told is the first derivative. So this is the first derivative of x that we're looking at right here. But a couple things. Note, since the first derivative is cubic, it must be that the original function is quartic. So a 4th degree, when you took the derivative, brought it down to a cubic. So that's important. So we're going to have that W looking thing in the end. And it's going to open upward because this is the typical way that a cubic goes. So the original function is also going to have a leading coefficient that's positive. So we're going to have a W heading upwards. All right, the bigger note is this though. It's a first derivative chart is less abstract and a lot easier to work with than this graph. So I think it's worth taking the time to just say, okay, forget the graph, it hurts the brain. Let's just go right to a first derivative chart. Now we know that the first derivative is going to have critical points where the tangent lines have slopes of 0. So we know that the, okay, I just screwed that up. I'm going to come back for a second. And I forgot what we were looking at, that this is not the original function, this is the first derivative. So forget those little tangent lines that I did. Here's the thing we need to take a look at here. Right here, this is where the first derivative is 0. So sorry, the first derivative has a 0 at 1, 2, 3, 4, 5 at -5. So we know we have a critical value at -5. And then what we think about is this first derivative function is below the x-axis down here, so its values are negative. So the first derivative takes on negative values below -5, and then this first derivative function is positive after 5. So we've got positive values to this first derivative function after 5. Then this first derivative has another root, it's equal to 0 again at -2. So we know that what that means when the first derivative is equal to 0, there's a min or a max or a horizontal inflection point there. And then we can see that after -2, this first derivative function is going to take on values that are negative. So that means the slopes of the original function are going to be negative because the first derivative has negative values after -2. We have another root at 2 for the first derivative. So there's another critical point at 2. Now the first derivative function's below the x-axis. It's below the x-axis down here, which is negative. But after 2, the first derivative function is positive. So that means the slopes of the original function is going to be positive there. So again, when we're given the graph for the first derivative, I think it's more abstract than the first derivative chart. So just transfer this information to the first derivative chart, and then I think we got it made. So what we're going to do is, let's just scroll down here a little bit. What we're going to say is, okay, now let's draw a possible graph again for the original function. At -5, we have our critical point. And since the slope of the original function is negative and then positive afterwards, this must be a minimum. So we could say, oh, we got a minimum here, we have a max here, we have a min here, and life is good. And that makes sense that the graph is going to be opening upward. It's a W. So now we can just sketch the graph, and we can say, okay, below -5, we got a negative slope until we get down here to -5, and there's a min there. And then it comes up to -2, and there's a max at -2. Then it swings back down, and there's a min at +2, and then it's going to go up like that. So this would be +2, and the graph might look like that. Sure enough, it's quartic, it's W, it's opening upward. But I think the big idea is this can hurt the brain. Let's maybe get in the habit of translating the first derivative function itself to a first derivative chart and go from there. A bonus, let's go back and identify the x-coordinates of all the mins, maxes, and inflection points, because you have to do some of that. Okay, now we know where the mins and the maxes are. Now, like a moron, sorry, I shouldn't say that, I have a bad habit of saying that, like a goofball that I am, I started in on this function. I just went right to the maxes and the mins. Now, wait a second, that's going to be the max and the mins for the first derivative. So hopefully we agree that the slope of the tangent line for the first derivative is equal to 0 at like -3. Now remember, we can think of the second derivative as being the first derivative of the first derivative. So the second derivative would give us a 0 at -3. That means that there's a point of inflection at -3 because the concavity is 0. And then the first derivative of the first derivative, which would actually be the second derivative of the original function, giving us concavity, would also give us a 0 slope here, would give us a min here. So this is at 0. So the second derivative is going to equal 0 at -3 and at -1. So at -3 and at, at 0. -3 and 0 is where we're going to get tangent lines that have slopes of 0, meaning the first derivative of the first derivative is going to equal 0. But we know the first derivative of the first derivative is the second derivative, giving us concavity. So we have 0 concavity, points of inflection at -3 and at 0. So that's how we can analyze that. All right, just a couple more problems. Answer the following based on this graph. If this graph is the second derivative of x, then on what interval is f of x concave up? Well, again, I think it's probably wise to say, let's just convert this to a second derivative chart, and we have 0 here, so at -2, and a 0 here at 1. We're going to have important values where the second derivative is equal to 0. We know the second derivative is equal to 0 when we have points of inflection. So we must have inflection points at -2 and at 1. And then beyond that, we know that now we have 3 intervals for this second derivative. The value of this second derivative function, it's above the x-axis, below -2 in the x direction. So these are positive values up here. So the second derivative is positive below -2. The second derivative is below the graph down here. So these are negative values for the second derivative until we get to 1. And then after that, the second derivative is positive. Since the second derivative gives us concavity, then we know that the graph is concave up. The original function is concave up for any x values that are below -2. The graph is concave down in the interval from -2 to 1, because there's inflection points here, and it's concave down in between those two. Then after we hit this last inflection point, the second derivative function is positive, the values are above the x-axis, concavity is positive for the original function, concave up after x equals 1. we got to get to the absolute mins and maxes on the intervals. If we look at this, let's suppose we're dealing with the interval that goes from -4 to 6. Then we can see that we have a relative max here and a relative min here. But in that interval from -4 to 6, can they be trumped? Can they be beaten out by the endpoints? The answer is no. This endpoint is not higher than the max or lower than the min. So this endpoint doesn't matter. This guy doesn't come into play either. It's the relative max and the relative mins that are the absolute maxes and mins, or the absolute max and min of this interval. So, so right here we'd have an absolute max at 4, and it would occur when x is -1, and we have an absolute min at wherever this is, -4 down here. So that would be the situation there. Now over here, if we look for the absolute max and min of this, we have a relative min and a relative max. There's no point on our interval, on the over the function on our interval, below the relative min. So this guy is the absolute min, but the relative max is beat out by this endpoint. So we would say that the absolute max in this interval actually goes up to 4. So the absolute max is here at 4. The absolute min is here at -1 in the y direction. Now let's go back and take a look at this situation. What if we say we have the open interval from -4 to 6? Would that change the absolute min or the absolute max? And the answer is it would not, because the endpoints, or nearing the endpoints, are not the high or low points along this interval. And we're talking about the absolute max and min of a function. We're always talking about the y value. It's all how high the graph gets or how low the graph gets. That's always the y value. We're talking the max of a function or the min of a function. It's the y values we're looking at. So that doesn't matter. But this guy gets interesting over here. It doesn't matter so much if we said that this was an open interval from -3.3 to 4.2, because I can't draw accurately enough to make that graph stop at 4. But anyways, so if we had an open interval here and here, again, that's not a problem, because those values coming in close to right there are not low enough to beat out this min. So this is still the absolute min. The graph comes down to a -1, so that would be the absolute min right there. But the problem becomes with the absolute max. This relative max is beat out by this part of the graph that's heading up this way. But now that this is an open interval, we have that weird situation where this function is getting really, really close to this 4 up here in the y direction, to the maximum y value being 4. But because it's an open interval, that function is getting super, super close to 4, but not quite making it. So we have no absolute max because we just keep getting more and more arbitrarily close to +4. Okay, big ideas in calculus. Since the first derivative gives us a formula for the slope of the tangent line for any x, if we set the first derivative equal to 0, we can identify critical points, which are mins, maxes, or possibly those horizontal inflection points. Since the second derivative gives a formula for the concavity of the graph for any x, if we set the second derivative equal to 0, we can identify points of inflection. We're almost done. This is the last problem right here. It's a problem like the ones in 7.5. Without using a calculator, find the absolute min and the absolute max over the interval from -4 to 2 of that bad boy right there. Well, if we set the first derivative, we got to find the first derivative, and we want to set it equal to 0, so we're going to factor it all the way down. This is the final factored form for the first derivative. If we set this equal to 0, then we can see that we're going to have critical points where x is 0. A critical point, if you set this equal to 0, then x would equal 3/2. So x could be 0, critical point, and the other critical point is -3. Now, if you think about it, remember, in an interval, the points you have to check are the critical points of the function in the interval, which could be mins and maxes, but you also have to check the endpoints to see if they beat out any of the critical points, any of the mins and maxes. So all we have to do when we get to here is we say, Here's our 3 critical points. They are all within the interval from -4 to 2. So the only other values we have to check in the function are at -4 and x equals 2, because those are the endpoints. Now, we could get sneaky and we could say, I wonder if these are mins or maxes. And you can figure it out, because this is a quartic opening upward. The first derivative would be a cubic that also has a leading coefficient of 0. So it's got to go whoop, like this, which means that it would go up to a max, down to a min, up to a max, and then off it goes. So anyways, it's, oh, I'm pointing to the wrong points, but you get the idea. But at any rate, we don't care. We don't really even have to figure out which ones of these are mins or maxes. We don't even have to rack our brain to do that, because whether it's a local min or a local max, ultimately we have to see if it'll beat these guys out anyway. So, so really it comes down to this. Check our 3 critical points and our 2 endpoints into the function. What am I doing there? We don't care. Oh, I guess I was saying that we'd have, again, these, the first derivative would be equal to 0 at these guys. So we'd have to check these values and then also the endpoints, but we don't care. Let's just go right to the final deal. All you have to do is put the 3 critical points and the 2 endpoint values for x into the function, see what value gives you the biggest amount and which value gives the smallest amount, and those must be the mins, the min and the max. So we can see that the biggest positive we get is here, so it's at a relative max at f equals 0, and then the smallest value we get over the interval is at this relative min. So that's the answer to our question, where is the absolute min and the absolute max? It is not at the endpoints, it is at one of the 2 critical points, and hopefully you see what I mean. It didn't even matter if we stopped to think whether these are local mins or local maxes. It all takes care of itself. Once you plug the value into the function, you just say, oh yeah, well it's a local min because it gave us a -49. Oh, that's a local max because it gave us a 5. So at any rate, that is a review of the first 5 sections of the unit. So hopefully we can do justice to this unit by the end of the week.